All right, so today we're looking at Taylor and Maclaurin series, very similar to what we started with polynomials, but now we're looking at an infinitely long version of them. So the general idea is still the same. We're creating a Taylor series by finding the different derivatives plugged in at c times x minus c to the power divided by n factorial. So same formula as we had for polynomials, except now we have this infinitely long series that we're creating for it. There are three main series you need to know. That's the Maclaurin series for e to the x, sine x, and cosine x. These are going to be series that you're expected to know just off the top of your head. We can go through the process of finding at least one of them, but the other two I'll give to you. So for example, for e to the x, we need to find if we want, let's say we want the first, 4 degrees or 3 degrees. F prime of x would be e to the x. F double prime of x would be e to the x. Third derivative is also e to the x. So that means f of 0 is centered at 0 because the Maclaurin series is 1. F prime of 0 is 1. F double prime of 0 is 1. And the third derivative at 0 is 1. All right, so we're just plugging in 1 for all the derivatives. So we have 1 plus x to the 1 over 1 factorial, x squared over 2 factorial, x cubed over 3 factorial, plus dot, dot, dot. Then our general term would be x to the n over n factorial. Now, what's the difference between this and a polynomial, aside from it being infinite, is that our polynomials are approximations. These are exact. This infinite series is exactly equal to e to the x. Now we have a series for sine and cosine as well. You can take the time to find these on your own if you want, but sine, it's going to be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial plus dot, 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 dot. And then the general term for this one would be negative 1 to the n, x to the 2n minus 1, plus 1, over 2n plus 1 factorial. For cosine, it's similar, except it uses the even degrees. That should be 1, and then x squared over 2 factorial, x to the 4th over 4 factorial, plus dot, 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 dot. Then negative 1 to the n, x to the 2n over 2n factorial. Okay. Now with these, we have some manipulation techniques. You can look up here for those manipulation techniques. But one of the big ones we can use is we can substitute into the series. So this is saying find f of x equals sine of x squared. Well, that just means it wants us to plug x squared into that sine series we had. So if we go back, sine was x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. So this one, f of x, is going to be x squared minus x squared to the 3rd, which is x to the 6th over 3 factorial, plus, and then x to the 10th over 5 factorial. It also, one of the first 4 terms, so we need one more, x to the 14th over 7 factorial. And then we also want a general term. We have x squared to the 2n plus 1 over 2n plus 1 factorial. X squared to the 2n plus 1 simplifies down to x to the 4n plus 2. So there would be our general term. Now, in part B, it wants us to find the Maclaurin series for f prime of x. That just means we're taking the derivative for each of these terms. So 2x minus 6x to the 5th over 3 factorial plus 10x to the 9th over 5 factorial minus 14x to the 13th over 7 factorial. And then the general term, if it asked for it, it didn't ask for it, but we could put it, and we just do the derivative like normal. We pull down the power, so negative 1 to the n times 4n plus 2 times x to the 4n plus 1 over 2n plus 1 factorial. Okay, and we should simplify these. So 6x to the 5th over 3 factorial just simplifies down to x to the 5th. 10x to the 9th over 5 factorial simplifies to x to the 9th over 12. And then anything bigger than 5 factorial, we usually don't need to simplify. All right, let's skip ahead a little bit. One of the other things we can do is we can use these in our alternating series error bound. Now this is one we talked about last unit. You can go back to last unit's video to find on that. But the general idea here is that we can use these manipulation techniques to find approximations that are extremely accurate for things. So, for example, like sine of x here, it wants us to approximate sine of 1. Well, without a calculator, that'd be pretty impossible for us without our Maclaurin series. So we know sine of x is the series x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot, 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 dot. Now this gives us a alternating series where the terms are getting closer to 1, and we can, or closer to 0, and we can plug in 0 here, or plug in 1, sorry, because we want to approximate sine of 1. Because it's alternating, that means for our approximation to be less than 1 over 1,000, we just need to find a term that's less than 1 over 1,000. So if we start plugging in 1, we're just looking for a term that gives us something less than 1 over 1,000. So we have 1 minus 1 over 6, that's not less, plus 1 over 120, that's not less. And then I just said we don't simplify factorials very often, but this is one of the cases where we would, otherwise how would we know what this term is? So 1 over 50/40. This one is going to be our truncated term. This one is less than 1 over 1,000. So we leave that off. We say, and we really should have used approximately, we should say sine of 1 is approximately this, which simplifies down to, I think, 101 over 120. Let me check real quick. Yeah, 101 over 120. Okay, and then it also has to justify, well, we use the alternating series error bound, so since, let's say 1 minus 1 over 6 plus 1 over 120 plus dot, 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 is alternating, decreasing, and has a limit of 0, then the error has to be less than or equal to the next truncated term, which in this case was 1 over 50/40, which is less than 1 over 1,000 by the alternating series error bound. Okay, part B just asked us to use our calculator to figure out the actual error, so we could see if we did sine of 1 minus 101 over 120, so our actual minus our approximation, we would get, let's see, sine of 1 minus 101, 120, oops. We'd get 0.00019 or 0.0002. So this is a pretty accurate approximation. We're within 2/10,000ths of the right value, which is a pretty good approximation for by hand, if I do say so myself. All right, you have the rest of, or you have the worksheet to work on. Please let me know if you have any questions. I'll be here before and after school as always. You have a great day.